Okay, let's begin. Welcome to the Atoms for Robotics webinar. Let's start off and look at the points I'll cover today. First, what's our main focus? Robotics design challenges that can be met with atoms. Then we'll take a look at who's doing this already. I'll show a few example case studies of robotics engineers using atoms. Then we'll find out how is it done. I'll talk about a key element for robotic simulation, how to represent control system within multi-body dynamics models. Then I'll take us through a brief demonstration of an atoms model of a tracked explosive ordnance disposal robot with an integrated controls model. Finally, we'll take some questions from the audience. So robotics is a very broad field of engineering, and there are many interesting applications such as space exploration, manufacturing automation, medical surgery, surveillance, unmanned flight, explosive ordnance disposal, toys and entertainment, personal assistance, and much more. As diverse as all these applications are, they share many of the same design challenges. And meeting those challenges with atoms means improving the design early in the process to avoid costly late changes, reducing test expenditure with fewer build and test cycles, and arriving at a better design by evaluating a much wider set of variations than possible physically. So what are some of the specific challenges? Loads prediction, be it due to the internal mechanisms themselves, external forces and tasks, such as moving heavy objects, or most often a combination of both. Robots can be subjected to severe loading while having aggressive design requirements for lightweighting and durability. This necessitates accurate load prediction, since without it, FEA stress and fatigue life predictions will be incorrect. Many robotic applications face design challenges common to vehicle systems engineering, such as tracked vehicle mechanism and belt dynamics, typical wheeled vehicle performance concerns like handling and ride targets, and aerospace vehicle requirements like landing gear function and flight surface controls design. Engineers have long met such challenges and improved such designs with atoms. The tasks for which many robotics applications are designed place them in challenging conditions. For example, mobility requirements for rugged terrain, heavy payload requirements, vibrational concerns in the way of loading or performance, such as damping requirements in sensitive surgical equipment. Meeting these individually can be challenging enough. Factor in the combination of these requirements, and engineers find that the system-level analysis capabilities in atoms are critical to success. The unmanned nature of robots naturally means that effective control system development is a must. And similarly, many robotics applications are unwired, so energy demand prediction becomes important. Engineers use atoms to predict, for example, the cumulative torque requirements for all the actuation and mobility needs of their applications. And finally, customizing robotics products for a variety of customer application scenarios and doing so quickly can mean won or lost business. Application engineers have come to rely on atoms for quick answers in these situations. Let's now turn to some specific examples of how real organizations are improving robotics engineering and their own stature with atoms. First, we have here a leading industrial robotics manufacturer, ABB. They use atoms to improve the speed and accuracy of their application engineering process. They serve a variety of customers, each with different requirements for manufacturing line robots. Validated atoms models provide field engineers the ability to confirm these custom configurations by running models through the required operations to determine functional success and important metrics like torque demand. Atoms models are also used to improve controller development such that they're tuned more correctly before entering physical trials, so costly downstream iterative loops can be avoided. Researchers at the University of Toronto's Robotics and Automation Lab used atoms to simulate mobile robots with track systems. They used a module called the Atoms Tracked Vehicle Toolkit, or ATV, to create the virtual prototype of an existing robot. The ATV toolkit was used for the dynamic modeling of the robot's track system in order to capture its flexible behavior and the interaction with its surroundings. The virtual prototype was validated using test results from the existing physical prototype. Simulations were done in different terrain conditions like flat ground, stairs, slopes, motion over obstacles, etc., in order to study the dynamic characteristics of the robot and in finding if the robot can safely negotiate the terrain. Many other useful results include motor torque required to perform these operations. Those can be also obtained. They can also use the same validated process to verify new tracked mobile robot designs for which there is no physical prototype available yet. Moving on, Pipetronics, now a part of GE Energy, they used atoms to model inline pipeline survey devices called pigs. So pigs travel through the inside of oil and gas pipelines for multiple purposes, including damage detection, so that pipeline engineers know exactly where critical flaws may be located along hundreds of kilometers of pipeline. Pigs can either be self-propelled or they can be pushed along by the flow of oil and gas. Typically, data is logged and stored using onboard recording systems. Failure of a pig is defined as when the pig gets stuck in the pipeline. Retrieval of a stuck pig may involve extensive undersea rescue missions, which may cost millions of dollars. It is disappointing but not critical if a pig traverses the pipeline but does not record data. Therefore, pigs must be designed so that they successfully exit the pipeline in all possible situations. Limited physical testing on short sections of pipeline, particularly turns and diameter changes, is the typical method for ensuring performance. Pipetronics pioneered the usage of simulation in this field when they developed and tested an atoms model of the pig to ensure mobility through crucial pipeline sections. Important loading prediction of the pig could also be performed with such a model. The Robotic Mobility Group at MIT has extensive experience designing, modeling, and controlling mobile robotic systems on uneven and rough terrain. With applications involving planetary exploration rovers, autonomous military vehicles, and automotive passenger vehicles. They find high-fidelity simulation of robotic systems with atoms to be a valuable research tool for their lab. By facilitating virtual prototyping of robot mechanisms and controllers, it allows them to maximize the value of their physical experiments. For example, they used atom simulations as virtual prototyping of a vehicle stability measure that they were later able to demonstrate experimentally. Atoms has a number of useful features that improve their research productivity. Models can be built directly in Atoms or imported from an external CAD package. For automotive applications, the Atoms car package includes numerous vehicle model templates and tire models that can be tailored to a particular vehicle. Once the 3D model is in place, it automatically considers dynamic effects such as gyroscopic torques, wheel slip, uneven terrain, and vehicle rollover. Coding these effects from scratch can take a lot of time. With the Atoms Controls plugin, they are able to connect their robot models to MATLAB and Simulink to simulate a closed-loop control system. This allows them to use existing MATLAB and Simulink code in conjunction with an Atoms model. They have used this feature to develop control algorithms for autonomous and semi-autonomous avoidance of both stationary and moving hazards. Hazard avoidance involves aggressive maneuvers in which many dynamic effects come into play. Using Atoms helps to pinpoint the problems before experiments and allows them to be more confident in their results. So, like those researchers at MIT, many engineers find it necessary to represent control systems along with their mechanical models so as to better understand their influence on each other. Often, mechanical designers and controls designers see and approach product design differently. But bringing those modeling domains closer together delivers a more accurate picture of the overall system earlier in the design process. So, design improvements can be made that would otherwise be difficult to realize. This is achieved in Atoms via a sophisticated mechanical system model and then coupling that with one of multiple options to represent the control systems. Let's now examine those different options. The most basic and straightforward method is to use a control law as a function for a force or torque element directly in Atoms. This is accomplished via the Atoms View function builder launched directly from the force or torque creation and modification dialogues. While these functions are continuous, they can be highly nonlinear. This approach is simple to implement and good for very simple controls models or even moderately complex ones depending on the skill of the function author. As the controls laws become more complex or numerous, other approaches are often preferred. For example, here we have the Atoms View Controls Toolkit, which provides tailored construction for basic control elements like filters, gains, and PI and D controllers. These elements are modeled as differential equations, and the user-defined inputs and outputs can be easily modified for later use with more advanced methods. Benefits here include ease of use in quickly constructing these most common control elements, more so than by the function builder alone. Another option is to use user-written Fortran or C subroutines containing the controls laws which can be linked to the solver and called by force or torque elements. This option is nice for its flexibility and is popular among those with existing controls in this format. Another use case is via the Atoms linear module, whereby a user can specify inputs such as control torques and outputs such as angular rates and errors, then export state matrices for the flexible plant after linearizing the model about a given operating point. These matrices can be exported in formats suitable for MSC's EZ5 software, MATLAB from the MathWorks, and Matrix X from National Instruments. Key advantages here are that the full power of control law modeling in the external software is available and has a good mechanical model on which to operate. This approach is often used as a starting point based on a sophisticated and accurate mechanical system model for the control system design process. Often engineers using in this fashion will proceed then on to one of the next two options to complete and finalize the control models. So let me show you those next two options. One such option here is co-simulation, which is enabled by either the Atoms controls or Atoms mechatronics modules. This allows for parallel simulation between Atoms and the control software, either EZ5 or MATLAB Simulink. This process looks like this. EZ5 is shown as the control software, but the process is the same for co-simulation with MATLAB and Simulink. EZ5 essentially starts Atoms, which loads the appropriate model, then both solvers initialize their solutions and then move to the first time interval, whose duration is defined by the user-specified sampling rate. EZ5 will run holding the Atoms inputs constant, and Atoms will run holding the EZ5 inputs constant. Next, the two exchange input and output state values and then repeat for the next time interval. This time interval, the sampling rate, should be a number of times smaller than the desired output step size. The output step size is how often you see result points in your post-processing. The size of that output step size really depends on the nature of the event simulated. Higher frequency phenomena, for example, will be better represented with a more frequent sampling rate between the Atoms and the control software solvers. So this is a very good way to improve and tune both designs, the Atoms mechanical system and the electronics, hydraulics, and/or pneumatics of the control system. This method provides the most robust solution and the highest fidelity overall system model. The last option I'll cover today is control system import. It is also enabled by Atoms controls or Atoms mechatronics. But here, Atoms solves the combined mechanical system and control system equations by importing an external system library, which can be generated by either MATLAB's Real-Time Workshop or EZ5. The external system library, or ESL, is used in Atoms, which automatically creates general state equation entities in Atoms. Here's a diagram of how that process looks. This method shares with the co-simulation method the overall benefit of a more accurate system model by virtue of the system-level approach and improved mechanical and controls designs. A unique reason that the control system import option is popular, though, is that the controls code is compiled when delivered to Atoms, which protects the intellectual property of the controls code. This, of course, is desirable in several situations, most often the supplier-OEM relationship, where the two must collaborate on the system-level model, but the supplier does not want to place their controls modeling source code at risk. Another nice part is that this can be accomplished in such a way as to maintain parameterization of the controls model once imported to Atoms. So the Atoms user can still perform design variation studies, which include important parameters of the controls model, such as gains, for example. To summarize these options, I'll map them against the Atoms product portfolio shown here. The first four options discussed are all available in the basic Atoms package. That's the force and torque functions, the Atoms View Controls Toolkit, user-written subroutines, and exporting state matrices. Co-simulation and control system import are available in the advanced Atoms package. Enabling technologies there are the Atoms Control and Atoms Mechatronics modules. Okay, I'll now go through a brief demonstration here in 4 parts. So let's begin the demonstration. Okay, so what I have here is a tracked robot, this explosive ordnance disposal robot. And what it's going to do is, scenario here is that it's going to investigate a suspicious package, perhaps it's a suitcase here, maybe a suitcase left at an airport or a train station, something like that. So let's take a look at the robot. On the leading end of the robot here, we have what we have here is a gripper claw. So it's basically two 4-bar linkage mechanisms, and then the wrist will also rotate the whole mechanism about one axis. It's watched via a camera that's mounted here, so that camera can keep an eye on what the gripper is going after. And we rotate around here, we can see a few other items. You'll notice this is a tracked robot, as I mentioned, so we've modeled the segments here with, those are rigid track elements, but with flexible connections between them, so discrete rigid track elements with connections defining the belt properties between them. Then here we've got a pivot point around the arm and the boom, so two key pivots for moving that claw around. And so we're going to focus on those pivots today. Those are the points where we're going to control and drive with a controls model. So turn the icons on here, we can see a little more detail around the track model there. Again, highlighting here that you can see individual force elements representing the flexibility and stiffness of the belt properties, and then contact elements between each of those belt segments and the ground. And now here, as we zoom in on one of the main pivot points we talked about, we can see that we have both a rotational motion and a force element here. The force element, of course, is turned off right now, and we're driving this with a perfect motion right now. Similar story is applied down here at the arm to turret pivot. Again, a motion and a force element available to drive that right now, and as it exists right now, a perfect ideal motion is driving it right now. But that's what we're going to go change. Okay, so let's get started and do that. We go to the Adams Controls plugin menu here, and that's where we're going to start. So from Controls, what we'll do is start with a plant export. So we've got a nice mechanical model here, a nice mechanical system model, and so we're going to take this model and export it, a plant version of it, export that out so that we have something to work on in EZ5, in the control software. So what the control software is going to need to know are key inputs and outputs. So this is coming from the Adams viewpoint. The inputs from the Adams viewpoint are torques to drive the arm and the boom. So that's what essentially Adams is expecting to come in from the control software. Now, outputs that Adams is going to provide for the control software, in this case, are going to include the angular positions and angular velocities of those arm and of the arm and the boom. And so that's what the control software will operate on. And here we can pick which control software we're going to use. I'll use EZ5 in this example, but same process really holds for running this with MATLAB. Select the solver choice and a couple other parameters, and then we're ready to export the Adams Controls plant. So we've done that plant export, and now it's time to move on and go into EZ5 and hook up the controls model. Okay. So, picking up where we left off, exported the plant, now here we are in EZ5. What we've got in EZ5 is a partially built controls model. On the left side here you can see command arm angle and commanded boom angle. So these are essentially position versus time, so angle versus time plots, essentially that we want to program in to have define how we would like the boom and the arm to move. And then we've got blocks here for a fairly simple controls model, a PI controller, and then we've got transfer functions on each end representing a first order lag that could represent some slop in the system, basically slop in the control system. So for the purposes of this demo, it's fairly simple controls model. Obviously with an EZ5 we can do a lot more. So the main thing we're doing here now is bringing in the Adams mechanism. So this is the plant that we just exported from Atoms. We're using the EZ5 extension to bring in an Atoms model. So we brought the Atoms model in, selected the model that we wanted to bring in, and there it is in the middle of our diagram. So now it's to connect that to the control system. So we're first connecting that model to the PI controller for the arm. So what we want to pass to the PI controller is the arm angle. We want to tell it what the arm's position is, and send that to that PI controller, so we can then calculate the error and make the appropriate adjustments. Similarly, we'll do the same for the boom angle. Now, this control system doesn't use those velocities, those boom omega and arm omega angular velocities, but we could have a more advanced control system that could operate on the velocities as well if we like. So now we need to connect these first-order lag elements to the Atoms model as well. So from there, that's essentially the last piece of the controls, controls loop that then provides us the arm and the boom torques. So here's the arm torque. So we want to pass that arm torque back to the Atoms mechanism. So there we are now driving the Atoms mechanism, driving that arm and driving that boom now with the torque that the controls loop deems necessary. And let me go in here and we can just change that arrow there so it looks nice and clean and symmetric. Alright, so our model in EZ5 is now ready to go, and the next step here would now be to send this model back to Atoms. Now, actually, the next step would really be maybe oftentimes folks will tune the controls model a bit right here within EZ5 using the representation snapshot in time of the Atoms mechanism that we had. But we'll pretend that's already been done here for time's sake and move on. And we're going to export now this model. And you can see what I did here. As I mentioned earlier, we can keep these design parameters, all these gains for the PNI gains and the gains for the lag elements and key parameters there. We've kept those parameters. We've exported this model now so that this DLL file here will contain those parameters in such a format that Atoms can read. And this little DLL file now, compiled code, I can't read, I can't do anything with visually, doesn't show me the guts of the control system, but I can now import that into Atoms, which is step 3, and operate on my Atoms model with it. So back in Atoms, here we go. We now come up to our Atoms controls menu again, and we're now going to import this control system. So first thing we need to do is define a name for the state equations, the general state equations that Atoms will create to represent the key elements of the controller, and then also select the external system library that we'd like to use, that control DLL, and then we need to assign the inputs and outputs for this basically for this controls element that we're creating. So we already did that, right, when we exported controls plant 1 earlier, so we'll just go ahead and select that one and say, yep, we're just going to use these same inputs and outputs. These are the ones that correspond to this particular controls model. And now we're ready to create the control system in Atoms. So I'll go ahead here, click OK, and there we go. We've external system libraries created. And so let's take a look at our model now. So go ahead here and zoom in on this model a little bit, and let's zoom in on those pivot points. So again, as I mentioned before, we had motion and a torque here. What we want to do now is look at this torque, and as we investigate this torque, what we can see is that the boom actuation torque element actually now is now, instead of just being a zero force, now is actually referencing a state variable called boom torque, which is being calculated by the control system, coming in from that control system model, I should say. And so what we need to do here is activate, I should say, the torque and deactivate the motion so that we let the torque drive the system. And we'll do the similar process down here at the arm to turret juncture. So we will deactivate that motion there, and now investigate the torque and make sure it is referencing a state variable from the control system. Sure enough, it is from the control system model that we imported. So it will all be solved within atoms. This is again sort of an example of the last option I showed you. We'll turn on the torque, and there we go. So now we've got torques defining the motion of the arm and the turret. Or excuse me, I should say the arm and the main boom. One other thing I want to take a look at before we simulate is show you again here that I mentioned we were able to export design variables right out of that controls model. You can see them here, these gains for the integral and proportional gains for the controllers, and gains for those lag elements are all listed here as well. So what we can do now is we can edit those in atoms if we would like, and run design studies in atoms on how sensitive the model is to those gains. Through all different events, right? Maybe in the control system we were only able to look at it sort of a snapshot in time from the model, but here what we'll be able to do is now look at it throughout the time history. Okay, so now time to simulate. So I hit go on the simulation, and of course, in the effort of time here, we won't wait for the simulation to run. That simulation for this model runs about 10 or 15 minutes, so it doesn't really take that long actually. But I've run a couple of runs now, and so what I'm going to do here is post-process. We'll just jump right to the fun part here and see what happened. So here's the first run I ran. First time I tried this, and so here's our again our model in the Atoms post-processor, where we can control all manner of things with regard to the animation. So as we start our playback, you can see here comes the model, here comes the robot, rolls along and approaches the suspicious suitcase here. The claw comes down and engages, and then we try to pick it up. Whoops, and it does not actually pick it up in this case. So we can zoom in on a different angle here and see if we can take a closer look and see what happened. So you can see the suitcase is kind of at an angle here, and the claw is at a bit of an angle, but a slightly different angle. So we're able to, when the claw grabs it, it actually does twist the suitcase around so that in effect it becomes a little more narrow. And what happened is the claw wasn't programmed to close far enough. That gap was too wide. We can see this again nicely here. There's our claws opening up, and it's these motions right here. There's a motion right there that's highlighting there at the base of the claw that basically defines how much movement the claw is going to have, open and close. So what we need to do is I went in and actually just added a few more degrees. Now those can be run from a control system as well. Right now they're just run from a perfect motion, but those again would be something we would want to model with the control system. So here we go. We try again now, and in this scenario I've actually tried to add a few more degrees to that motion, have it clamp down the claws a little bit more, and so we're clamping down again this time, and there we go. We pick up the suitcase, and we now have the suspicious suitcase in our grasp, and we can take it off to a safe area for further investigation. So we'll take another look at that and follow it here from the claw point of view. And an interesting thing here, not an interesting thing, but of note, I suppose, is that again these are standard atom solid-to-solid contact forces that we're using to represent these forces. So we can represent different levels of friction, and things like this as well when trying to pick up these cases to see how that's going to influence it. And there we go, successful pickup again. Okay. So, back to the PowerPoint. What I'd like to do is summarize here, and to do so, I want to point out that leave you with a few points. I'll point out that there are several design challenges in robotics for which atoms can be a tremendous help to the engineer in addressing. We talked about those. We also talked about the fact that many successful engineers are already doing this and already gaining a lot of these benefits. And finally, I want to point out that for many robotics problems, the integration of control system modeling with multi-body dynamics and atoms is a powerful approach to improving each domain's models and, more importantly, improving the results of the system-level solution. Okay, thank you very much. On behalf of MSC Software, I'd like to thank you for attending and viewing this webinar and remind you to register for upcoming webinars and events at the link shown. Also, I'd like to let you know that, of course, all these webinars are recorded, and you can find all these webinars here at the web address here at webinars.mscsoftware.com. And so please share this information and pass this along to your colleagues that were unable to attend or view this. Thank you very much.